Hello everyone, welcome back to the lectures videos, and in this video we're going to talk about a Taylor series. Okay, so in the previous lectures videos I have talked about the way that we use the geometric series. We use the geometric series to let me do the lectures for you. Okay, we in the last lectures videos we have used the geometric series to obtain some kind of power series for some rational function. We also uh, use that. We also use that technique to help us obtain some power series for the log function, for the inverse strict function, and so on. Okay, and the thing is, like I said, we want to represent the function. Thing is, we want to represent a function by the power series. Okay, and one of the way that we have done is we use the ideas of that we can kind of describe the rational function by the geometric series. I mean, if you have something a little bit different, like you have 1 plus x, then you have 1, you can rewrite 1 plus x as 1 minus x, and then you put in the power series. If you have the ln of 1 plus x, then you can think in the way that ln of 1 plus x is the antiderivative of 1 plus x, 1 over 1 plus x, and you replace 1 over 1 plus x by this power series, and you integrate the x to the n, and by doing that, you will have the power series for the log function. This is one of the way, okay? You try to 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 construct the power series for the other function in terms of some series that you already know before. Okay, but actually there is the more rigorous way to write down the power series for the function. Okay, and I believe that we have done this thing before because I mean several weeks ago we have talked about the Taylor polynomial. So there's no big difference between the power series and the polynomial. Okay, the thing is for the Taylor polynomial, you will have the approximation for your function, and the Taylor polynomial is just the polynomial of degree n. Okay, that means you have finite terms. But for the series, you're gonna have you have infinitely many terms. Okay, and I mean that means you have the infinite sum. But the thing is, it's quite similar. So for instance, let's suppose that you can represent your function f of x in terms of the power series over here. Cn x minus c to the n, where Cn is some sequence, when Cn is a coefficient, and you try to expand your function about the point C. Okay, that means if you want to expand your sequence your function about C, that means the main core for your function should be x minus C to the n. Okay, and the point is, like I said, you need to know the coefficient. Okay, if you want to, the thing is you need to know the coefficient. So for instance, over here, the coefficient is -1 n to the power of n plus 1 divided by n is your coefficient. For this function, when you write out the parallel series, -1 to the n is your coefficient. So you have to determine the coefficient if you want to describe your series in terms of, if you want to describe your function in terms of series. Over here and over here, for instance, if I want, so that okay, so that means I need to find C0, C1, C2, C3, C4. Is it familiar with the thing when you do the Taylor polynomial? I mean, exactly the same thing. So for instance, if you want to find C0, you just need to plug C in both sides. If you plug C in both sides, then C minus C give you 0, C minus C square give you 0, C minus C cube give you 0, The only term that is not zero is the first one. Okay, so C0 will be the output of your function at C. Okay, C0 is the output of your function at C. Okay, so starting from here, if you take the derivative of your function, okay, so f primes of x, so C0 vanish when you take the derivative. The derivative of x minus c is 1, so you have c1 times 1. The derivative of this terms is you bring 2 into the front, you have 2c2 times c sometimes x minus c. The next term you have is c3 x minus c to the power of 3. So you bring 3 into the front, you have 3c3 x minus c squared, and so on. And the thing is, if you plug c into this equation, then f primes of c equal to c1. Over here, when you plug in c for the second terms over here, when you plug in c, you have c minus c, which is 0. You plug in c for the next term, you have c minus c squared, which is also 0. And you repeat the process. Everything's over here. Every other term will be 0 except the first one. So in general, C1, the coefficient C1 will be determined by the output of your first order derivative at C. Okay, it's exactly like the Taylor polynomial. And the same thing, you differentiate again, you have the relation between some power series and your second order derivative. You plug in C, the other terms will be 0 except, every terms will be 0 except the first one, 2C2. So over here, you can say that the coefficient T2 in your power series will be given by the output of your second derivative at C divided by 2. Okay, and you do the same things again. So over here, the general formulation to compute every coefficient in your power series will be, if you want to compute Cn, okay, you need to compute the nth order derivative of your function. You evaluate that nth order derivative at the points where you expand your series. Over here, I expand my series at C, so I plug in C into my nth order derivative function for the function f and divide by the n factorial. Okay, over here, if you repeat the process, you have C3 equal to 1 over 3 times 2 times the 1 over 3 times 2 times the third order derivative at C. Okay, this is C3. Okay. Over here, it's the way you formulate your Taylor series. It's just exactly the way you do the Taylor polynomial. You try to compute your derivative, and this derivative will help you compute the coefficient in your series. But instead of having the nth degree polynomial, you will have the polynomial of the infinite degree. Okay. 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 So if f has a power series expansion about the center C, then the Taylor series will have, then your series should have the formulation as f the nth order derivative at C divided by n factorial times x minus c to the n. Okay. For every terms in your series, it will be corresponding to this coefficient. Okay, so you have f of c. If you write down this thing explicitly, you have when n is 0, you have f of c only. When n is 1, you have the first order derivative divided by 1 factorial, which is 1 x minus c to the power of 1. When the index n is 2, you have the second order derivative at c divided by 2 factorial x minus 2 to power x minus c to the power of 2. Then when n is 3, you have the third order derivative at c divided by 3 factorial x minus c to the power of 3, and so on. You repeat the same thing. And this power series is called Taylor series. Okay, because the way you obtain it, it's just like the way you do the Taylor polynomial. And if the centers where you expand your series is 0, then you have the Maclaurin series. Okay, that means you have f of 0, f prime of 0, x minus 0, x minus 0 square, which is x square, f double prime at 0. You have f, the uh, the third order derivative of f at 0, x minus 0 to the power of 3, which is x cubed, and so on. And if you write down your expansion at c equal to 0, then you have the different names Maclaurin series. Okay, it's just a special case of the Taylor series. Okay, over here, the question want you to find the Maclaurin series for the function e to the x, sine of x and cosine of x. So I mean, remember that in the last videos we have determined that the power series for the function for the exponential functions is over here. Okay, but we obtained in the it just by intuition, because when you write down this series, you have this thing, and when you take the derivative of this thing, you have the same thing. So we recognize that we recognize that this series does not change when you take the derivative. So that means this series should represent for the function that have the same property, which is e to the x. So I mean, I just conclude that this series is the power series for the function e to the x, but I didn't prove rigorously. Okay, I just say that by intuition. Okay, we have this series is e to the x, but over here we're gonna find the Maclaurin series for this function in the rigorous way by this theorem. So over here, let's go into the first one. Okay, so we want to find the Maclaurin series, so that means you need to find the series of n starting from 0 to infinity of Cn x to the n. Okay, and the thing is you need to figure out Cn. Okay, you need to figure out C0, C1, C2, C3, C4, and so on. Okay, you need to find the general formulation for Cn. So over here, we don't have a lot of way to do. So let's let's start with f of x. So f of x is e to the x. Okay, f of x is e to the x. So from here, f of 0 is e to the 0, which is 1. And if you still remember, f to the f of 0 will be c0, the first coefficient. So from here, c0 will be 1. Next thing, f primes of x. F primes of x is also e to the x. So that means f primes of 0 is e to the 0 again. So you have c1 equal to 1. Okay, and then you do the same thing. You have f double primes of x equal to e to the x. Okay, therefore f double prime of 0 is e to the 0, which is also 1. So C2 will be f double prime of 0 divided by 2 factorial, which is 1 half. Okay, remember that you have the fact that the coefficient Cn is the nth order derivative at c divided by n factorial. Okay, where c is the points where you write down your expansions. Over here, the question wants us to write down the Maclaurin series, so the c is 0. Okay, the centers of our expansion is 0. And what if I consider the third order derivative, and when I take the derivative of this function, I still have e to the x again, and the third order derivative at 0 will be e to the 0 as well, which is 1. So that means the coefficient 3 will be the output of the third order derivative at 0 divided by 3 factorial, which is 1 divided by 3 factorial. Okay, so over here, over here, I should write down in this way. C1 is f prime of 0 divided by 1 factorial. So I have 1 divided by 1 factorial, 1 divided by 2 factorial. So over here, you can see that if you repeat the same process, so f for for C1, you have 1 over 1 factorial. For C2, you have 1 over 2 factorial. For C3, you have 1 over 3 factorial. So if you keep repeating the process, for instance, for the nth order derivative, you're gonna end up with the same thing, and you're gonna have Cn equal to 1 over n factorial, okay? Because the rules keep continue, okay? The pattern keep continue. C1, 1 over 1 factorial. C2, 1 over 2 factorial. C3, 1 over 3 factorial. So Cn will be 1 over n factorial. So that means your series should be, okay, so over here, you have figured out the pattern for Cn. And once you know Cn, you can write down your power series. So the function e to the x can be rewritten as the series of n starting from 0 to infinity, Cn x to the n, and Cn is 1 over n factorial. Okay, so this is the power series for the function. This is the Taylor series or the Maclaurin series for the function e to the x. Okay, how about the next one, the function psi of x? Okay, how about the function psi of x? For the function psi of x, okay, again, you need to know the fact that you want to write down the power series for this thing. So the power series for this thing is Cn x to the n, and setting from 0 to infinity. We have the Maclaurin series. So your expansion is about, will have x minus c to power of n, and c is 0. So you have x to the n. And again, remember that if you want to obtain the power series, you should know you should know the coefficient Cn. Okay, and for the coefficient Cn, I would say that you have f of 0. F of 0 is psi of 0. So you have 0. So from here, C0 will be f of 0 divided by 0 factorial. So you have 0. Okay, how about C1? Okay, remember that you need to know Cn. And to know Cn, you need to compute C0, C1, C2, C3, C4, C5, okay? And then you find the pattern so that you can compute Cn, okay? And over here, f prime of 0, sorry, uh, over here, f of x is psi of x, okay? So f of 0 is over here. The next thing, what is f prime? The next thing, you want to compute C1, okay? You want to compute C1, and C1 is f primes of 0 divided by 1 factorial. Remember that this is the general formulation to compute Cn. Okay, so you need to know f primes of 1, and to know f primes of 1, you need to know f primes of x. So f primes of x is sine of x prime. So you have cosine of x. Okay, so f prime of 0 is cosine of 0, which is 1. So from here, C1 is f prime of 0 divided by 1 factorial. So I have 1 divided by 1 factorial. Okay. And next one, I need to compute C2. C2 will be f second derivative 2 times divided by 2 factorial. So I need to know the second order derivative of f. So the second order derivative of f is cosine of x taken one more derivative. F prime of x is cosine of x, and I need to take one more derivative. So I'm gonna have negative sine of x. Okay. And from here, f double prime of 0 is negative sine of 0, which is 1. I'm sorry, which is 0 again, because sine of 0 is 0. Okay. So C2 is 0 divided by 2 factorial, which is 0. Okay. And for the next coefficient, which is C3, you're going to have the third order derivative at 0 divided by 3 factorial. So I need to know the third order derivative. You need to know the third order derivative function. Okay. The third order derivative function. Okay. So I just need to take the derivative of the second order derivative. I have negative sine of x, taking one more derivative, then I have negative cosine of x. So from here, f of the output of the third order derivative at 0 will be negative cosine of 0, which is negative 1. So C3 will be negative 1, the 1 divided by 3 factorial. Okay. And the thing is, now you can see that you now you can see that if you repeat the process, the anti the, I'm sorry, the I mean, if you want to compute C4, you need to find the fourth order derivative, and the derivative of negative cosine of x is sine of x again. So once you have sine of x again, the patterns will continue. The patterns for these four things will continue. That means you're gonna have for the pattern for the f n of 0, okay, gonna be 0, then 1, then 0, then negative 1, and then you will start from 0 again. You have 1 again, you have uh 0 again, you have negative 1 again, and then you have 0 again, you have 1, 0, and negative 1. Okay, because you can see that what for the sine function, it will become cosine, negative cosine, and if you take one more derivative, it will return to sine again. So the pattern will repeat in groups of 4. Okay, 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1. So this is the pattern for your numerators. For the denominator, it just become 1 factorial, 2 factorial, 3 factorial, and 4 factorial. So the thing is, um, Cn Cn will be Cn will be um, negative 1 to the powers of 2m plus 1 divided by 2m plus 1 factorial. Because you can see that, the thing is, you can see that for the terms that have the even index, it just becomes 0. Okay. For the terms that have the even index, it's just 0. So you just care about the coefficient for the terms that have the odd index. Okay. And because you have 1, negative 1, 1, negative 1, 1, negative 1 alternating, so I have negative 1 to power of 2m plus 1 divided by 2m plus 1 factorial. Okay, so over here you can see that you just have 1 factorial, 3 factorial, and for C4 it will be 0. For C5 you will have 1 divided by 5 factorial. Okay, so I just have the factorial for the odd number. That's why I have 2m plus 1 factorial, and I don't care about the even term. I just care about the odd terms. So in general, I have the function psi of x given by the series and starting from 0 infinities of -1 2 to the 2n plus 1 divided by 2n plus 1 factorial times x to the power of 2n plus 1. Okay, like I said, the coefficient the coefficients for the even term are always 0. So you don't have x squared, you don't have x to the power of 4, you don't have x to the power of 6, you don't have x to the power of 8. You just have x to the power of 3, x to the power of 5, x to the power of 7. That means over here, if you write down this thing explicitly, you're gonna have x divided by 1 corresponding to n equal to 0. When n equal to 0, you have -1 to the power of 0. I mean, if you write out this thing explicitly, you're gonna have x divided by 1 minus um minus x cubed divided by 3 factorial plus x to the power of 5 divided by 5 factorial minus 6 x to the power of 7 divided by 7 factorial and so on. Okay, you can test with different index and you're gonna see that you have this power series. Okay, and how about the power series for the function? How about the power series for the function cosine of x? I mean, you can do the same thing. You're starting with cosine, you take derivative, and again, the cosine function will repeat the patterns in the groups of 4 again. Okay, so you can come up with this power series. You can come up with the similar thing like the sine function, or you can do this way. You can do this way as well. Like we know that the cosine function is the derivative of the sine function, and the sine function have the power series as x minus x cubed divided by 3 factorial plus x to the power of 5 divided by 5 factorial minus x to the power of 7 divided by 7 factorial and so on. So when you take the derivative of this thing, you're going to have 1 divided by 3x squared, 3 factorial plus 5x to the power of 4, 5 factorial minus 7x to the power of 6 divided by 7 factorial and so on. So you're going to have 1 minus x squared divided by 2 factorial plus x to the power of 4 divided by 4 factorial minus x to the power of 6 divided by 6 factorial and so on. Okay. I mean, 3 factorial is 1 times 2 times 3. So 3 cancel out with 3, give you 1 times 2, which is 2 factorial. For the 5 factorial, you have 1 times 2 times 3 times 4 times 5. 5 cancel out with 5, give you 1 times 2 times 3 times 4, which is 4 factorial. So over here, you have uh, the power series for the cosine function. And if you want to write out this thing in a more general way, you can have n starting from 0 to the -1 to the 2n and x to the 2n divided by 2n factorial. Because you see that you just have over here different opposite to sine function. The power series of the cosine function just have the even terms, like 2, 4, 6, 2, 4, 6. So I have 2n factorial. Okay. Okay, I think the video is quite long, so I will continue the material in the next lectures video. So I will see you in the next lectures video.